Hi, so welcome to this video, and today I would like to talk about size reduction and especially about mills and crushers. So for today we have the following plan. This is that you get a basic understanding of mineral mining and its significance. At least very shortly I would like to use it as a starting example and look a little bit into it. And from there you learn about the general operating principles of comminution systems and also their classification. Okay. I hope I will be able to deal with the word comminution, which is for me always tricky. I don't know why, but comminution, so far it works well. And at the end, you get a first overview about different comminution systems and which are used in industry. Okay, so the general principles and what kind of systems we are using. And with this, I would like to show you this slide, and this is the global mine production of minerals. And this ranges from 1901 to 2023, so more than 100 years. And here are some selected materials like bauxite, which is used, 95% of bauxite are used to make aluminum. We have chromium, cobalt, copper, graphite, lithium, and you see how we process and mine more and more of these materials over the years. And it's more or less always an exponential growth. So we mine more and more materials, and some of them we mine for already a long time. And for lithium, for example, you see a huge increase in the last years, which is due to electromobility. Also the rare earths, which are very important in batteries and smartphones and so on. You see the huge increase here. We have silver, here's coal. Coal is probably the problem with getting data for this time. You have to assume. And with gold, which is also extracted, and iron ore. So we produce more, we consume more, so we need more materials, and this is basically exponential for all of them. I selected them a little bit randomly, but you will find this for other materials which are not in the list. So I would look a little bit more into gold as one example for all the materials you see here. And the question is, how do we get gold when we mine? And this is what you see in this chart. And so the first is that we mine ore. And maybe one of you recognizes the picture or the game from where the picture is. If you recognize this, write the answer in the comments. When I was young, I played this a lot. So we have gold. This is a gold mine, so we're mining gold. And the first thing we have to do with the ore, where the gold is in, is that we have to crush it. And crushing is comminution, and comminution is the topic of the lecture. So the first step we have to do to get our gold is to crush the ore in multiple steps. So we start with a jaw crusher. At the end we have a ball mill, and this is what you hopefully understand after the video. And here is our unit operation for today. But to learn a little bit more about mining, so when we have the crushed small particles, they have a large specific surface area, right? Because they are smaller, so I can try to get the gold out of the ore. And first I have to introduce some lime, and this lime at the end gives a slurry. The lime is needed because we need cyanide, and cyanide is a very dirty chemical, and if we don't stabilize the pH to more than 10, we will get hydrogen cyanide, and this is something you don't want to have. It's very toxic, and therefore we need to stabilize the pH with lime. This is what's happening in the thickening process. And then we go to the leaching, and in the leaching the cyanide comes, and the cyanide has one very cool property, and most of the cyanide we produced is used to get gold because it extracts the gold out of the ore. So the gold sitting in the ore goes now into a cyanide complex, so the gold goes from the solid into the solution. It's the same happening when you make coffee. The caffeine sits in the particles, the water comes and solves the caffeine into the liquid, and here the cyanide solves the gold, forms a cyanide complex and goes into the solution. And now we have the gold in our solution, and then we add activated carbon. And the gold complex, gold cyanide complex, now adsorbs to the carbon particles. So it goes from the ore to the carbon particles. And the advantage is that the ore is, even after crushing, much larger than the carbon particles, and it's easy to separate both of them. So we have our carbon particle carrying some nice gold. And then we need some acid washing. And in the washing, basically, because not only gold complexes go to my carbon, but also some other metals or some other stuff flying around in the solution. And at the end, I just want to have the gold. So I try to clean my active or my carbon in an acid washing. And then it goes to a carbon elution. And this elution is basically, again, a washing process. So you have a water solution with, again, some cyanide in. And with this, you remove the cyanide gold complex from the surface, and it again goes into solution. And then we go to the electrowinning, and this is an electrolysis. And in the electrolysis, now we break down the cyanide gold complex, and the gold is free and goes to the cathode. And from the cathode, we can scratch it as gold sludge, and this gold sludge is then melted, and then we have gold bars. The concentration is not perfectly high. It's about 60-70%, something like this, depending on silver content and so on. But you could concentrate it even higher. And similar processes are for other minerals which we are mining. And here you get an idea how energy intensive the mining of gold is. But since we improve technically, we are able to process even ores with a very low amount of gold economically. So here you see we need 12,000 kilograms of rock. So this is 12 tons of rock. And from there we have 2,500 kilograms, so 2.5 tons of ore, gold ore. And this contains 4 grams of gold. So to get a nice ring, like this marriage ring or the Lord of the Ring ring, we need 12,000 kilograms of rocks. And we can do this still economically. I don't know if it's a good idea, but we can do it. But I also would like to go to a little bit, or to another example I already have in the videos, and this is coffee. So coffee has to be grinded, right? I have a grinding machine here because we talk about size reduction, comminution. So this is the system doing like this. And in coffee grinding, basically the grinding determines the taste, right? So we have the size of the coffee particles from coarse to fine, and then you see you get an espresso or you get a filter coffee or whatever. And this is mainly determined by the grinding, so by the comminution. So with these two examples, I would like to start about size reduction of particles. And size reduction, which is generally named comminution, means the state of dispersion of a solid or liquid substance is changed by overcoming the binding force, which can be physical or chemical, works both, in the original particles that smaller particles are formed. So I have my coffee particles, I have my ore, and I put it into a comminution system. And then I break the bonds in the particle or between the particle. So it could be a chemical bond in the case of coffee grinding, and in the case of ore, it's mainly chemical bonds. But also the coffee powder could stick, and then I break the physical bonds, and at the end I get smaller particles. And you have to think, because if we talk about construction materials, where we have sand, gravel, crushed stone, cement, clinker, and so on, we have specified grain sizes which are required. So the industry, the government gives us sizes we have to achieve. So we have to do it by the requirements. For food products, for example, such as grains, stones, spices, sugar, meat, and so on, they are normally crushed for further processing, so that we can do more with them, that we still can, for example, extract the cacao from the fruit, right? Metal and coal ores are ground in preparation for separation process. This is what I have shown you. And materials are also grinded for mechanical activation, because if you crush a material, the surface is fresh and activated, and you can make something with it. So this is very general about size reduction. And we have a lot of different systems which we use for this step or for this unit operation, and basically we can say that these different comminution machines use different mechanisms. So we have machines using compression, and we have machines using shear. So for shear, I would have, for example, this machine here, and this is applying shear, as I will show you also later on another slide. Then we have impact. This is another coffee mill, and this is an impact mill. And basically in the impact mill, we have a rotating blades which crush the particles. We have cutting. So the cutting mill is, for example, if you have copper cables, you want to recycle copper cables, then you cut them, which is the best comminution mechanism for them. You can have hydrodynamic shear from a fluid, or you can also have shear in the particle. When you heat it or when you apply an electric force, you can get shear, which finally breaks this particle. So all the devices which you get to learn or which we're using in comminution are based on these principles. So whether they're using compression or shear or impact, but I already can say it's not that clear, even if I try it, to say, okay, this is 100% compression, 100% shear. Very often in machines you have multiple of these events, even if one is the major event. So the fundamentals of particle fracture is important that you understand. The basic is always one individual particle. So we have one particle, right? So I have this huge particle, very tough to crush, but the basic is always the fracture of this one material. So particle fracture results from externally imposed stress fields. These are the slides before, which may originate from various type of mechanical loading, and they are strongly, the fracture strongly depends on the material properties, right? You can imagine this rock is really hard to crush because it's a very strong material. And then it's important that the fracture process exhibit local stress intensification at notches and micro cracks, which serve as initiation for cracking. So if I apply a force on this particle, stress lines will go through the particle. And if I have a crack or a hole somewhere, the stress line has to go around the crack in the material. And this means around at these notches, the stress lines are densified. So the stress is increasing. So if I have a perfect material without any failure, it's very strong because the stress lines can go equally through it. But if you have somewhere a notch, a crack or something, the stress lines have to go around, they intensify, and the cracking starts there. And this is how particles crack. So the energy input required for comminution is significantly greater than the increase in interfacial energy resulting from surface enlargement. What does it mean? So if I crush a particle, I will get 2 or more new particles, and these new particles in total will have a higher surface area than the first one, because I release surface area in the particle. So if I crush this guy, I will have at the end more particles, and all particles together will have a higher surface area than this one. To create surface, we need energy, right? Surface energy. However, it's not that easy that I can just say, even with some theories in another video we will talk about it, make this assumption to say, hey, I know the new surface area, so I just calculate the increase in surface area, and this is the energy I need to crush it. No, because we have plastic deformation, we have rearrangement, we have heat which is generated, and energy goes also into this. So a lot of things happen at one particle, and this is the fundamental of fracture. And here it's a quite nice diagram, because in this diagram you see glass beads, and the glass beads are shooted onto a wall, and then they break. And multiple of these glass beads are shooted, and then the fraction of broken beads is counted. So for different sizes and different velocities. So if we take here 8 millimeter, the large glass beads, And then we see at a low impact velocity, like 12, 13 meters per second, around 7% break. And if we increase now the impact velocity, so we are shooting them faster, the amount of particles which will break increases up to more than 90%. Okay, because we have more energy, which when the particle hits the wall, and then it will break. And also we see that the smaller the particle gets, the more velocity, so the more energy we need to break the particle. If we look at these 100 micron particle, and we have here the highest velocity for 8 millimeter, we cannot even crack one of the small ones. So we have to shoot them faster, faster, faster to get sufficient breakage. Why? Because the smaller the particle, the less cracks and errors are in the structure. And this means it's harder to crush it. So large particles very often have cracks, holes, disturbance within the material, and this makes them relatively easier to break. And the smaller the particle, the harder it is to break, because the material gets more and more perfect. Good. So if we go now from one particle to a bed of particles, and this is what you see here, one particle and multiple particles, like the coffee mill, for example, right? So we have to separate this from the individual particle fraction. And even if the individual particle fraction is the basis and happens in here, we have now additional effects. And this means in a bed of particles, multi-point loads are acting. Because I'm pushing from here and here, so two forces acting. And I could do the same, but the particles also, when they are compressed, they are also pressing against each other. So this guy will not only feel the force from the top and the bottom, but also from the left and the right, right? So in the bed, particles, multi-point loads are acting. And then part of the shear stress is compensated by applied compressive stress. Higher energy to fracture is needed. And this is because you now compress the bed, and this needs energy. And this energy you don't have anymore for breaking, so you need more energy. And also part of the input energy is dissipated by compression and particle movement, right? Because now you compress the bed, you have the particles moving around, and this takes energy. So therefore, fraction in a bed of particles is different and needs more energy than the fracture of a single particle, even if the fracture of a single particle is still the basic for this system. So, what can we do now with these comminution systems? We have different ones. I talked about the mechanisms they are applying, but we also have to consider that we have, for example, a huge size range. And this means that comminution happens for very large and up down to very small particle sizes. And our systems have to be able to deal with this. Then we have also very high mass flow to very low mass flows, right? A few kilograms to hundreds of tons per hour. Size reduction can happen in dry as well in liquid processes, right? And in the best case, if we have a liquid process, we would love to dry and classify, separate all in the same process. And this cannot be done by one system. So we have a huge range of expectations, so we need different systems. And the easiest separation is to talk about crusher and milling. And this is why the word comminution is so important, because comminution means milling and crushing. But crushing means a crusher, milling means a milling, right? So how can we distinguish now between a crusher and a mill? And this is what you see here. So basically here is the particle size. And we can keep it quite easy, so we group it by size. So huge particles, 10 millimeter and larger, are done by crushers. And small particles is grinding, and grinding is done by mills. So we have coarse crushing, fine crushing. Coarse crushing would be the jaw crusher, right? The ore from the gold, first coarse crushing, and then we go very down to fine grinding. So this is a very first system, mechanism how we distinguish between grinding and crushing. And for crushing we take a crush, and for crushing we take a crusher, for grinding we take mills. Okay, and now I would like to look a little bit into the different systems. So when we first start with compression, and we start with very large particles, we have what you see here is a jaw crusher. And a jaw crusher works with a single particle. So fracture basic is the fracture of one particle. And you see it also in this nice GIF from Wikipedia. So mechanical pressure is achieved by the two jaws of the crusher, of which one is fixed while the other reciprocates. So it moves. So this means the particle falls down, it sticks, and then you crush. You have smaller ones, they fall down, they are sticked, you crush. And they are very commonly used for hard and medium hard materials as rock, slag, ores, and they can crush down to 10 millimeter coarse or 100 millimeter if it's a coarse crusher, or 10 millimeter if it's a fine crusher. And one very important value is the size reduction ratio. And they can have a size reduction ratio up to 8:1. So size reduction ratio means the size here as the ratio to here. So 8 times the size leads to the final size here. And these crushers are very often used as the first crushing when you have ores or large rocks or something like that. Okay, so a second one is, and this is probably something you also know, is a roller crusher or a roller mill. And here we see that the same principle can be applied for a crusher or for a mill. The principle is the same, large materials, small materials. So two equal sized roller rotating inversely with a fix the gap between the rollers. And this is used for soft, medium, also hard materials. So we have limestone, iron ore, coal. And the coarse crusher for large materials, they have cams. Fine crusher have smooth rollers. But here it's also written, it has proven advantage to comminute bulk materials between roller presses in a material bed. So this means while the jaw crusher can work with individual particles, here we saw that roller crusher works much better when you have a bed of material, as you see nicely in this picture. Not individual particles, but a bed of particles is crushed. And you can get very high throughput with these machines. And another advantage is you also can crush material which is wet or humid. However, if you have very hard materials, since the throughput is so high, the abrasion is also high. So the very hard material is not the best used for this here. And when we look at size reduction ratio, we can go from 6:1. Okay. And the last one I would like to show is as a cone crusher, and I have a cone crusher here. This is the coffee mill I already showed a few times, and this basically works as a cone crusher, and it implements the back and forth motion between the fixed and moving tools in a circular manner. So here's the cone, and the cone is turning around, and then the material goes down and crushed. And in an industrial level, we have an offset. So this means this is not perfectly straight, but it's a little bit dancing around. I don't need this in my coffee here, because here it works also straight. But in industrial scale, we always have these dancing around, and then we always get material flow. Crushing cone, which is slightly inclined from the vertical, executes a gyratory motion with the crusher. And this gives continuous flow through the system. And in size reduction ratio, this is a little bit better. So 10:1, and it's also more used with smaller materials compared to the jaw crusher, for example. Okay, let's have a look into different mechanisms, and then we can talk about shear. And for shear, I would like to talk about the ball mills, even if some other mechanics also happen in the ball mill. So the ball mill consists of a hollow cylinder rotating about its axis. So this is the cylinder, and the cylinder is turning. Also, it's a little bit inclined normally that the material goes through. It is partially filled with balls, and this is the grinding material, are these balls, and steel, stainless steel, and so on is used. And you can imagine if it's turned, the balls are going up and then they're falling down and they are moving. And what you basically get is the crushing of the material between the grinding media, between the balls, because of the movement of the balls. So the balls is hitting the material and they are also shearing the material, and the movement of the grinding material, which is critical here, depends on the rotation speed, the filling angle, and so on. It works very good for brittle materials like cement or processing, and these ball mills, we have them in our lab, can be very small, but they can also be very large and work on multiple 100 tons per hour. And a huge advantage is this size reduction ratio to 100 to 1. And these ball mills are very often used as a last step because of this high size ratio. So you have a pre-crushing in gold, you have a pre-crushing with a jaw crusher, and then you use a ball mill, and then you have your ore, which you can go into the next step. Okay, a last one I would like to show you is an impact device, and the impact device could be a hammer crusher or a mill. So the material is stressed by very fast rotating tools, which are fixed or movable instead installed on the rotor. So here you hit the particles, and this is a very old method. So principle of operation was used already in the Middle Age. So jaw, cone crusher, and so on are joined around the beginning of the 20th century, and are now, of course, also a nice tool. But this principle of operation for the hammer crushing is something we use already for a few hundred years. So the high mass of the rotor rotating speed is 20 to 60 meter per second for a crusher. For a mill, it goes up to 120 meter per second, and this gives a size reduction ratio 20 to 1, and especially you get in the size distribution a large amount of fines. Okay, also the different machines can give different final size distribution, and this hammer crusher, hammer mills give you very large amount of fines. They are mainly used for soft and semi-hard materials because they effectively can destroy them, and materials with plastic deformation behavior can also be used. And it's also good when you have mixed materials where you want to get on the single components. These impacts or hammer crushers, hammer mills are very good to use. Okay, so here I would like to give you a final overview about the discussed systems. So we have the jaw crusher with a size reduction ratio from 3 to 1 to 8 to 1, and they work with coarse materials, and they are mostly the first step. Roll crushers have a little bit better, and mills have a little bit better size reduction ratio, 4 to 1 till 6 to 1, and they are good for soft to medium hard materials, wet materials, high throughput. Cone crushers have even better, 6 to 1, 10 to 1, and they are very good medium to fine crushing, right? As we have the cone mill, the cone mill for coffee, and the hammer crusher, which has a size reduction ratio from lower than 20 to 1, creates a large amount of fines. And finally, the ball mill with a very high size reduction ratio. Is it good? Is another question, but a very high size reduction ratio, lower than 100 to 1. And this is often the last step for very fine crushing. This table is not complete. It's just for you to get a little bit an idea of what we discussed the last minutes ago. And therefore I would like to end the video. So I hope you get a basic understanding of the mineral mining process, and it's significant, right? The exponential growth of mining and the process of how we get gold from ore. You learn about the general operation principles of comminution systems and their classification, impact, stress, shear, and so on. And I hope also you get a first overview of the different comminution systems, a hammer mill, hammer crusher, jaw crusher, ball mill, and so on. And with this, I would like to end the video. And if you have any questions, please feel free to contact me. Thank you.